Hello, everyone. So I'm happy to give you an update on some recent work at Chara, and that was surprising to us of seeing changes in this very inner disk at the dust sublimation for at least a few Herbig Ae B stars. So this is work that was largely drawn from a thesis by Ben Sederholm, who's not here today. He works at Heidelberg currently, but he couldn't come today. But Jehan and Nuria and Stefan and Nura are here at this meeting, so there's other people you can talk to about it, in addition to the whole Chara team. Okay, so real quick, I know you've been seeing a number of slides of the inner disk, but let me just quickly go through the bullet points needed for this talk. So, Herbigs have these weaker magnetic fields compared to the T-Tauri. That means that the inner disk comes all the way in, not to a co-rotation radius, or some other magnetospheric radius, but to really where the dust is sublimated. And this leads to, partially this, and others lead up to this puffed up inner wall and a size that depends on the luminosity square root. The longest baselines data from mostly Chara, but also some supporting work at VLTI suggests also there's emission coming from inside. Although we're not you'll hear more about that in a talk tomorrow, I think, or I forget, maybe tomorrow, Nora's talk. And so the scales we're talking about are, if we want to get into within 1 AU, we do need long baseline interferometry, in the visible or in the infrared. So again, you've seen these scales, but 0.1 AU at 100 parsecs is 1 milliarc second, which is roughly the resolution of VLTI and Chara. So we're, again, going to all be looking at this hot wall of the inner disk, mostly is how we're interpreting mostly what we're looking at in my talk. So there's lots of evidence before interferometry of a dynamic inner disk. So this probably shouldn't have been a big surprise, really, to us in interferometry. It's just that we didn't have good enough data to hope to look at this until recently. Photometry, of course, shows variability in young stars where you have to be based on the time scales, and the behavior of the light curve suggests it's modulation of the wall or of the inner disk close to the star that causes line of sight variation. So that's been known for 10 or 20 years. Catherine did some work with Spitzer showing where you see a seesaw pattern in the SEDs of some objects, which suggests as the inner disk grows. And when we say grow, it generally means it gets taller and brighter overall, that you can see some effects of implied shadowing of the outer disk where the mid-infrared goes down. So the inner disk goes up, the mid-infrared goes down. So that's seen in a number of objects in her work, and others, Sitko also worked on that. There's also been, there's also a lot of interpretation of shadows cast on scattered light disks seen in adaptive optics and chronography and HST images. Often they're static, coming from misaligned disks, so there's a whole nother interesting field aligning the interferometry of the inner disk and scattered light disk based on misalignments and seeing the interesting shadows. But those are generally static on our human time scales. But here we can see evidence, for instance, in this work, where you can see there are some small shadows in this ring which are moving around and changing with time. So something probably close in. That is the heights of the disk, again, as a possible idea. And lastly, there has been some data from the VLTI, in particular, showing some changes in the inner disk on the few objects that they've been able to do so far. But the timescales of this have generally been not very suitable for interpretation. They've generally been, kind of retrospective when you're analyzing data taken over many years and you're trying to fit a model and you realize there are some huge changes. Until recently, we would always be able to combine data over many years to do a model in interferometry, partly, because we had no other choice. But now we're starting to see that for some objects, this is a terrible idea and can't be done. So this was one of I think, the best work. There's been some other work, but this was the main work really showing very strong asymmetries. And this is in the source I'm talking about today, over 1 year period. But long enough period that you can't figure out, of course, the cause. Is it changing every year? Is it changing every day? Is it, how common is it? So this is the sort of beginning of a new business, that we're going to be getting into as we look at more objects. Our object here is MWC 275 or HD 163296. This is a favorite Herbig Ae star, about 2 solar masses, 9200 Kelvin. 100 parsecs away. It can be seen by both the northern and the southern hemispheres, so it has a lot of great data. In the scattered light, there's also been seen changes in the shadowing variations for this object. So in addition to that inner stuff I just showed in the inner disk, it's been seen in AO, again, but with very irregular time scales. So not really able to see if it's stochastic or smooth changes or whatnot. This is one of the few Herbig objects with an observed microjet. So this is an unusual object, so in certain ways. So we're going to be, all right, it also has some great data from ALMA. So this is the ALMA D-sharp image by Zella et al. So on this, so you see this, you see some of the same rings, plus ALMA sees a ring that we don't see in scattered light. So we're zooming in here by a factor of 100 or so. And so just to, again, orient ourselves why we need interferometry, this is all happening on inside this little, red dot here, right? So we're going to shift scales quite a bit now and zoom all the way in, way beyond what you could ever do with ALMA or super ALMA or super VLA or anything, right? This is really a unique domain of spatial resolution that right now really only can be done with VLTI and Chara. So here are some 4 model images done before this work. So these are mostly based on a combination of single baseline data, thrown together with radiative transfer models. So these are radiative transfer models back in 2008 based on Chara data. And Miriam did some work at the VLTI, coming to similar conclusions. This is showing this inner emission. So Miriam and Ajay both found that the data needed this inner emission, which is, again, subject to a second talk. And then this is some more data taken with VLTI and Chara, which tried to do more imaging, or not so much modeling, but more on the imaging side, and found it to have a lot of emission coming close in and didn't even see signs of a ring. Now, we now know that some of this was due to a combination of lack of resolution and also averaging over time. That way, if you average too much data over time and it's changing, it can make something that's actually a ring look like a Gaussian because of the smoothing effects that happen, from random sampling of a changing curve. So even though these look rather Gaussian now, we have more data now showing that it isn't so Gaussian. But again, we have to now go back and think about some of our older papers and some of these subtle effects that we didn't even know, we didn't know they could happen based on the assumption that they were static. So we need to do a little rethinking of the old data, I think. And that's the data I just showed you from Joel. So conclusions from this earlier data was that it's interesting that the inner disk is actually quite aligned with the outer disk, not always the case. So it almost is exactly the same as the outer disk within errors, within degrees. I mean, very much the same. And again, we have evidence for emission inside the dust wall, and again, multiple lines, many techniques showing us changes on the 1-year time scale. So here's real quick. Someone already asked a question about the difficulty in imaging, so I'll put a slide here. What we try to do is combine data from the VLTI and Chara if we can. This is showing the VLTI data in this darker color for this particular epoch. There's longer baseline data, but this was one particular epoch that we had, so we only had shorter baselines. And then the Chara data, this is the best coverage we can get, which we don't often get it this good. So that's one problem too. When we combine data over multiple nights, they're not always the same quality data. Some may have only 5 telescopes, some have 6, some have VLTI data, some don't. So it's a pretty complicated process, and so you do have to be aware that there can be artifacts or problems with some epochs. This is why a lot of this is what we call evidence for changes in the context of the big picture, but by itself is not as good as we would like and we're heading towards. So this is one of the images that we have. You have a star in the center and you have some kind of a ring, but it's kind of spotty and there are these lumps and bumps on it. The bright features, we don't know always if it's artifacts from the big gaps in our UV coverage or if it's real. So this is, again, why we need to have multiple epochs and try to combine UV coverage. So I do want to say why we think it's real. This is showing different ways to do the imaging. This is an imaging method that VLTI uses a lot, where you fit a shape like a ring and you let it modulate. You kind of have a ring and then you have sine waves that go around it. And it's a way of doing parametric imaging, so to speak. And you see a lot of VLTI images like this. So that's what you have here. And then these are 4 different imaging methods have different regularizers, different authors, different artifacts, presumably. And the idea here is to show that at least many of the features are in common. And work continues on this. Here's a recent image that Fabian Baron showed is working on using more neural network-based, a neural network-based system here. So again, kind of shows the same thing. There's a bright feature, and it's a one-sided arc. Is kind of similar to all these methods. We can also, in a few cases, image with two different interferometers. So here's a case where we had some very long VLTI baselines for some other epoch, I forget what, July 20th, and you see it looks kind of like two lobes here. And if you look at the Chara data from the same exact night now, just we have now 50 or 2 times the resolution, here's the image here. So you see that it's pretty compatible, a little sharper image with the Chara data, some small changes, but this to me really made me happy, that we can, with very different resolutions and UV coverage for these simple objects, we can often get good images. Now, can I guarantee every epoch will be this good? No, because the data quality varies. So just, if you see one image and you see a bump that isn't there, I'm just going to tell you it's probably an artifact. You kind of have to look at the whole ensemble. So this is our 5 nights at taken over 6 days. So this is our best chunk of data here. And again, what we think we're seeing is an asymmetry that starts in the upper right. And that, again, it's not perfect data, but you can see that it seems to be slowly moving down clockwise as you go along these 5 nights. So it's amazing that we could get this kind of temporal coverage with Chara. And like I said, some nights, like this night, we had a combination with Pioneer. We always included some Pioneer to help regularize the short baselines, but sometimes we had exact dates. And so what we see here is a rotation clockwise, and it's good that is the expected rotation rate because from ALMA and other information we have, so that at least that makes sense. And just to say, if we get a 44-day period from that, which is about 4 times slower than expected from Keplerian motion, which is supposed to be 12 days. So you've heard some of this. I just will show a movie that Jehan worked on. One idea is if there's a planet further out that was somehow causing a spiral wake interacting, that we would potentially see it. And Jehan is working on seeing, putting some simulations behind it to see if that's really true. And I'm not an expert, but there's, Mario and Zhaowan also have potentially explored ideas that could explain this too. So we need to work on it. So I will just say there's a lot to continue on this. So I think it's going to be a really exciting new field for us in interferometry. With VLTI, of course, we want to go, and Charlie, we want to look back at these two objects. If it's a planet or if it's real, of course, it should probably be permanent, not be episodic. We can try to combine it with AO imaging and look for shadows moving to see if we can connect the two directly with some simultaneous data. We can, of course, do a much larger sample now and observe a bunch of targets with now few day separations to see if we see this. Could we even see bracket gamma? If there's a planet there that's accreting, could it potentially escape the embeddedness of the disk? Probably not. But there's data exists on the hard drive. We should look at it. And I should mention, there's also going to be J-band data coming from both VLTI, the Bofors instrument, and Chara. So that will give us more resolution to help again with interpretation. So I think that's all I have. So thank you.
Thank you. So we have time for questions. Who wants to go first? Yeah.
Jack Lissauer, Ames. If you have unresolved data, just to show time variations, is that useful? Unresolved data at other wavelengths or whatever, just to have an idea where you are perhaps where you are in the cycle. I mean, I know it's not going to be perfect, but has that been used?
I mean, we can now try to look back at a few targets and see if we can pick out signals. Obviously when it's kind of face on, any rotating features won't really show a very strong signal. So, most of the past, they've always been the star being obscured. If you just have the right angle and you see, you can get very strong absorption effects is usually what's seen in the past. So seeing it in emission in the infrared, maybe if there's a precision infrared photometer in space that we could, do at some point. For a survey, yeah.
Okay, so probably I will use the time to ask. All
right, so I've been on 20 years of your students' committees.
Sorry.
Now that we're seeing, no, it's great stuff. So now that you're seeing there's time-resolved data, there were conclusions that were made in the past about sort of the shape of the wall and so on and so
Right.
forth.
Yeah.
So do you have to, all that stuff has to be revisited, but do you have any information then on the shape of the wall, or is it all just this time variability?
Yeah. So we'll definitely hear about some shape that Nora's going to talk about for this source because it's more face-on, and so it's a lot easier to deal with. So, yeah, for MWC 275, we haven't gone that. We've focused on this dynamic change, but we do want to now try to, you know, you have to, again, it makes it a lot more complicated now that you have to worry about spots. You can't just fit a simple model, which is what we all did and all do. So, yeah, it's going to make life harder if a source is variable. But we don't know if every source is variable. You know, we're picking the ones that are. So this is, again, why we need to do more blind surveys where we look at objects. I should mention that VLTI, even though it has less resolution, can show that it can really do this stuff, as I showed for a few objects. You can't do the details as much, but you can definitely see which side is brighter than asymmetry with VLTI, and then you can see if that position angle is rotating, right? So it's very, I mean, as long as it's dominated by like one spot. So if it's something like a planet-related phenomena where there's probably like one thing that dominates and it's in orbit, I think it's clear. If this is coming from complexity, like some accretion-related instabilities or some, you know, vortex instability or something that might be a little bit more chaotic, then it may be difficult with the VLTI, and you'll see position angles jumping around and won't move smoothly, and then you'll probably need Chara to kind of try to pick it out into blobs and interpret it better, right? So it's kind of going to be a team effort, I think, of the two interferometers to make sense of the next stage. Yeah, this only took 20 years, so yeah, another 20 years we'll understand this.
Okay, very good. So let's thank John again. Thank you.